Thank you very much, Cheryl. Thank you. Hi, my name is Justin Shenk, and I'm going to introduce to you some of the lessons I've learned in the process of building an app for doing facial expression recognition and deploying that. So just to get an idea who knows what here roughly or what your interests are, who's trained a neural network before? Okay, cool, a little more than half. And who's helped with putting a model into production before? Okay, that's another fraction. So cool, so hopefully there's something to learn for everybody. I would say I've learned a lot in the process of building this, and since I'm the only thing separating you, like Errol said, from cocktails, we'll try to wrap this up. Feel free to ask questions at the end. So yeah, facial expressions, when we talk about emotions, in this case specifically, we're limiting the discussion to facial expressions, but a lot of the lessons that can be learned here apply equally to NLP or to other types of sentiment analysis. So this is kind of a spoiler alert. The end product from this project is a web interface for splitting a video into frames and then doing facial expression recognition on the frames. So this is roughly what it looks like. You can download the code. If you go to the GitHub, Justin Shenk /deepemotion, you can download the code, play with it yourself, run it on your own server. And the way it works, basically, so you can see in the browser how the facial expressions are identified in each frame. So the question is, how do you get something like this to run in a production environment? So I'll give you an introduction about me, my background, what brought me here. We'll talk about some emotion detection use cases. We'll go over some of the neural network architecture points, because that's quite central to this topic, and how to implement that in a Flask website, which you can then productionize with gUnicorn and Docker. And then after that, we'll have questions if there's time. So my background, I've been working on this project with Peltarion as a field data scientist. I've been focusing on computer vision and also some NLP applications. Just because scientist is in the title doesn't mean I can't work with emotions. It's kind of the stereotype that the Asperger's autism spectrum is more appropriate for people who are scientists and engineers, but I think this is a very interesting topic. What does Peltarion do? If you've heard the talk earlier from Anders Sharpteg, or if you've been living in Stockholm and interested in AI, you've probably heard about what product is built there. It's a deep learning model builder. So you have basically like a graphical user interface for identifying the layers, building the architecture, version control of models, and rapid prototyping. So my background is I was doing neuroscience research in the US, interested in the brain and understanding how is it that we're able to do basic functions, most everyday things. It's amazing how it works. Then I switched to something, eventually I switched to something that was less complex, like machine learning. I was doing work in web, so I built an Open History project, which is a crowdsourced platform for translating stories of like first-person interviews of human rights abuses. And I've been working also in the past as an independent contractor. I developed an application for Intel using facial expression recognition, demoed it at ICML, NIPS, CVPR, and CBIT the past 2 years. And I'm a contributing writer for O'Reilly, Journey to AI and Machine Learning for Your Business. So the application that this all springs from was a pet project of mine a few years ago called Party Pie, which this is an image from NIPS 2017. And the game goes, you take a picture and it says show happy, and then it ranks the players based on their ability to show that happy emotion. So it was a lot of fun. Also, my introduction to learning to code with TensorFlow, how to build a web app connecting all these parts. And I've continued work with Peltarion, doing research on neural networks and how do you understand, like, explainable AI, how do you understand the deep neural network architecture and how to optimize it. And we'll talk a bit about that afterwards. So why facial expression recognition? So this is a topic that it came to me out of a hobby, out of a game that I was playing with my flatmates. Hey, let's take a picture and upload it to the Microsoft API and see what emotion they say we're showing. But it's actually, in broader society, you have many applications that are coming out of the woodwork. So for example, if you go to Piccadilly Circus, you might notice there's 2 cameras above the gap sign. These 2 cameras are detecting faces. And they're able to use this data to provide better services for customers watching the advertisements. But if you can use a little bit of imagination, you can imagine that this is only a start with how AI can be applied in society. And facial expression is probably the next step in terms of reading signals. So where does the interest lie in the business world? It's a $20 billion industry, according to a post in The Guardian. And everything from potentially autism therapy, so helping people to understand the signals around them, social signals, to market research. So people are watching a YouTube video, and how do they react from that? This is actually quite interesting for businesses to automate this, because some industries have been doing this by hand labeling images for years. Most of this work derives from the work from psychologist Paul Ekman, who, there's a group where you could hire him to hand label frames from images, but that takes way too much time if you're dealing with video. And there are actually really good data sets publicly available, so you can bootstrap a project quite easily. So quickly, if you're going to go down this path and you have a need to figure out, okay, when I start, what kind of direction do I go in? Am I just doing Jupyter notebooks? You're probably going to want to start with infrastructure for training. So if you can choose the Peltarion path. If you're the business leader and you say, I want to get this solved really quick, I want to click a button and have it done for me, do that. If you're an engineer and you want to build it yourself and understand if you've compiled CUDA and you don't mind doing that again one more time, use a GPU container, for example. It'll save you a lot of headache, too, if you use the containers, because that way you can make sure that your TensorFlow versions are compiled for a specific context. When you're choosing a data set, you want to choose a data set that actually reflects the audience that you're dealing with. So it might be that you're trying to label a data set based on users who are maybe not showing a wide range of expressions, like Spock here. And you want the data set to represent what you expect to see in the field. That kind of goes without saying, but it's useful to remember as long as we forget it. So we actually have access to a really nice data set for prototyping. It's called FER 2013. Some of you might have used it already. And it's 48 by 48 grayscale images, so fairly low resolution. The images were scraped from Google Image Search by Google, by researchers at Google. And they were able to quickly create a data set, then go through, hand label it. I think there was a PhD student hand labeling it. And assigning a label to each of those images, one of these 7 categories: angry, disgust, fear, happy, sad, surprise, and neutral. The thing to notice about this is the ground truth. Like, what's the ground truth? This question comes up a lot in this field. What does actual happy face look like? And this this kind of labeling question comes up a lot with these subjective metrics. So it turns out that the humans on average will get 65% right, the labels that were assigned to these images, plus or minus 5%. And the top accuracy of any models trained, in this case it was a Kaggle competition, was 71%. So a quick deep dive into how it is that we're able to go from images to the representations for a deep neural network. We convolve an image filter, a kernel over the input image. So the kernel would be the gray in this case, this gray square matrix. And you convolve that over the blue input image, and you create a feature map. And the feature map is a low-dimensional representation of the image, which you can pass on to the network. So, OK, so you have the idea of how to extract some features from your data. How do you build your network? And one of the first challenges that I found was when I started building neural networks, I really had no idea how big a network should be. There was very little explanatory guidelines. Why should it have 1,000 units instead of 2,000 units in a given dense layer? And if you ask around, people will tell you, meh, it works. It happened to be that my mentor told me, make the model as big as it can be, and to keep the accuracy up, and then start to shrink it. So that's one way to go with it. There's a lot of heuristics in this field, as you probably have heard. But yeah, definitely using prior work is the best place. It's the best place to start. So optimizing. So as a somewhat of a tangent, this really bugged me that I couldn't explain why this number was better than this other number. So I worked on a research project, which led to a current preprint paper with Anders Harpteg as co-author. We have tried to quantify exactly what is it that determines the goodness of the width of the layer. So if you're interested in that or applications around that, I recommend check out Delve. It's a PyTorch extension you can get on GitHub, or check out the archive paper. Just download it. So the neural network model that was actually used for this web app, it's about 5 convolutional blocks. So it's pretty standard. As you get your feature maps out from the convolutional layers, and you do max pooling and batch normalization and dropout. And it turned out that in this case, no matter how much bigger I made it, it didn't improve the accuracy. So this was where I say, OK, this is a good enough size. And the accuracy for the model that was used here was about 67%. So I was like, OK, not bad for not having to do any tricks, just using out-of-the-box Keras layers. OK, now we want to start training our model. So one thing to notice when you start training a model is your accuracy is the one thing you definitely want to get up, but you have to pay a lot of attention. Like in this case, I was surprised that my accuracy was 90%. That was much higher than the highest reported accuracy. And then I noticed one thing is that the loss function I was using was somehow left on binary cross entropy. The reason that was an issue was because the model was expecting, OK, every time that it's, instead of saying assigning credit based on how correct the label is, it was saying, is it this one label or not? So is it happy or not? And then it compared everything with regard to that one label. So the loss function here is really crucial, that it matches your target problem. After fixing it to categorical cross entropy, then we were able to get back on track, and it converged to 67%. During training, this is something that you'll find probably in the exploratory phase. If you don't have enough data for a specific class, then you can do some things like class balancing. So in this case, there was very few instances of discussed. So you can actually see, in this column, the actual of those was quite low. So if you want to counter that, you can do things like class balancing. So after you've after you've trained your model to work on images, you want to get that to work in a production environment where you might be dealing with videos. So the first thing you do is you take those videos, split it into frames. Then you have to detect the frame from the face from the frame, and then pass that face, like a version of that face, into the network. How to detect faces? There's multiple ways. If you're tied to Python like I am, I love being tied to Python. I try to use it for as much as I can. There's 2 kind of out-of-the-box ways to do that. So OpenCV, the computer vision library, has a har cascade classifier. So it's the one that's been around for 20 years at least. And it will identify based on the combination of dark and light patches in an image what the face is. But there's some limitations to that are worth addressing. So rotationally invariant. You can't turn your face and expect it to work. And it's also sensitive to lighting. And the benefit is that it's quite fast. But if you want to improve the precision, like you do in this environment, in a production environment, you're going to want to use something that's more powerful, like the MTCNN. So MTCNN is another network that is specifically trained for identifying faces. And it works with rotational variance, and it works with different lighting conditions as well. But it is slower. So depending on your trade-off, the good news is once you have your whole service containerized, you can scale up, spin up microservices that correspond to each one of these. And then finally, you're going to want to be able to serve responses as a service. So in this case, we're using a Flask endpoint. So some of the things that you can do in optimizing this is, OK, what are your degrees of freedom? And one of the degrees of freedom that you can change is the input size of the image as it's passed into the network. So here's some examples, some benchmarking showing that if you change the scale of the input image, how does that affect the accuracy? And for a happy image, for example, it's able to detect much faster with a lower resolution image, but the accuracy of the prediction vastly decreases. So it's useful for figuring out, OK, this is one of the variables. How do we optimize for this one as well? And then, OK, so you got your model trained. You have an idea how you want to do the inferencing. But how do you serve that actually into a Flask endpoint? There's a great blog post write-up by Adrian Rosbrock, who talks about how to serve a Keras endpoint, Keras and a Flask endpoint. And he said one thing not to do, and I'm guilty of having tried this, was to load the whole entire model graph during the response. So if you load it within the context of the response, of course, the memory is going to fill up that one time, and it does not automatically notice that that's in memory. So you have to let the server know that, OK, these model parameters are in memory, and this is how I can find them so that I can pass the images through them. There's a few tricks for doing that. Initially, I went to making a global variable in Python. That's not optimal. So then finally, what I ended up doing was using TF serving. TensorFlow serving will actually handle all this for you. And if you used something like, anyone here use BERT as a service, maybe? Yeah, I know a few of you. Good. So BERT as a service takes care of the magic of this for you. So you really don't have to think of, if you're doing NLP, TensorFlow serving generally takes care of the part about, OK, how is my memory being managed? How do I handle multiple concurrent requests? So it's a good place to start. And yeah, so if you wanted to implement this yourself for fun, say you build a pet project and you want to run TensorFlow serving with an emotion classifier, you can go ahead and pull the image, Docker pull Justin Shenk emotion serving, or just add to your Docker compose file if you're using Docker. After the image, the name of the image, and expose 8501 and 8500 ports. And then you've got basically production level API for facial expression recognition. So some of the middle points that can save time possibly in this path. I developed a Python package called FER, which has a sole purpose of taking an image as input and identifying the face and exporting it with the bounding box. And then there's an additional feature where you can detect the emotions inside. So it's optimized for rapid prototyping if you want to just play with it, connect it to a Raspberry Pi, and start making some fun projects. And yeah, if you want to give it a try, let me know if you have any questions about that later. So we've got the overview from getting our data, training it, knowing about how to put it into Flask, maybe put it into Docker. Now we want to be able to scale up multiple parts of the services. Maybe we want to scale up the face detection model independently of the emotion detection model. So one way to do that is with Kubernetes, for example. and it's useful for monitoring as well your application, finding out where your peak loads are and doing load balancing. So generally, lessons learned, select the data set that best matches your use case. Also, if you're doing deep learning, this is something where you can really benefit from asking for help, especially because there's so many people who are really interested and passionate about advancing AI, and you can gain so much from learning from other people's mistakes or what they've experienced. Definitely isolate dependencies with the containers as much as possible, so you can, your data science team will be really happy if you can say, okay, this is input, this is output, and they won't have to worry about, say, the back end. They won't have to worry about the web provisioning of GPUs and so forth. And build prototypes fast. Like definitely, anytime in a business situation when you can show this is what this can do, this is why we should put more time and energy into this topic, the sooner that it gets in front of someone who can appreciate the kind of visual aspect of it, the more likely the project will succeed, in my experience. So I want to say thank you very much.